Okay, so what I'm going to do is go over some electron configuration and orbital diagrams. I'm going to just give you kind of an overview first, and then I'll get into a few examples. Now let's start with this particular picture here. This is for a beryllium atom, and I know it's beryllium because if I look at the arrows over here, I see 4 arrows, and beryllium is atomic number 4. It's got 4 electrons. Because if you've got 4 protons, and electrons, for now we're going to assume they're always equal. In any case, we've got 4 electrons to focus on. Now look at this picture. You can see kind of the reddish, pinkish, purpley color here, and then you've got more of a blue around the outside. This is where the electrons are placed in this particular atom. The first thing we do is put 2 electrons in this s orbital. So the first energy level is in here, and there's 2 electrons there. And we designate that with this particular picture. Now these are in boxes. I usually use lines. It doesn't really matter. Lines I think are easier. But anyways, those 2 electrons in the first energy level and the s sublevel, which is the only C-type that you see in row 1, the only sublevel there is the s level, so they have to be in there. Then, remember we have 4 electrons, there's still 2 more to place. The next 2 can't fit in the first energy level because it's maxed out. The next 2 go out here and they zip around in the second energy level. Now, they both fit in the s sublevel because this particular orbital can hold 2. There's no other orbitals, and it's maxed out at this point. We don't even need to get into the 2p sublevel at all because we've placed all 4 electrons and we're all set. If we did have to put more electrons, if it wasn't beryllium, if it was something more than beryllium, then we'd have to see the p's come into play. So here's carbon. Now on the periodic table, carbon's got 6 protons, therefore it's going to have 6 electrons. So we have to worry about putting 6 electrons somewhere in this atom. So let's start off with the lowest energy. Remember Aufbau principle, you have to start with the lowest energy first. So 2 electrons are going to go here closest to the nucleus. Remember the nucleus is right in the center here. So there's 2 electrons. So we write 1s. We could summarize this and write 1s2. Then we have to put the next 2 electrons. Then we move on to the 2s, which is this sphere. Remember, s's are always round, so we put 2 electrons there. So we've got our 2 arrows, and we could summarize 2s2. There's 4 of our 6. This means we have 2 more electrons to go. Now we're going to put them in the p sublevel. Now in the p sublevel, we have, and you could ignore that, and that. In the p sublevel, there's 3 seats. There's p1, p2, and p3. And even though we know there's only 2 electrons left, we're not going to use all our p seats. We still have to draw either 3 lines or 3 boxes or 3 circles, whatever you want to do to indicate that they're different orbitals. So if you look in the picture, you see the purple or the dark blue color, you see the green, and you see the pinkish color. Those are the 3p orbitals. Remember, orbital holds 2 electrons. So 2 in the blue going this way, 2 in the green going in that direction, and 2 in the kind of pinkish color would be a max of 6. So p can hold 6, but in this case we only need to give it 2 because that's all we have left. We have all 6 electrons accounted for. We have 1, 2, 3, 4, 5, and 6. So if I was to summarize, I would write 2p2. And if you notice, we've stressed this a little bit, the valence electrons are the electrons in the outermost energy level. So in this case, it's over here in the 2s and the 2p. So you add up the 2 and the 2, and you get 4 valence electrons. Those are the ones who get to play the bonding game, and it also happens to match the group number. So if you look at where the where carbon is on the periodic table, it happens to be in group 4. So then you know you did it right. Let's take a look at the next element. This is oxygen. It obviously tells me it's oxygen, but if I didn't know that, I could just count up the arrows. 1, 2, 3, 4, 5, 6, 7, 8. And if I look on the periodic table, what element's got 8 protons and 8 electrons? That would be oxygen. So I know it's oxygen. In any case, same thing we showed you before. Here's the first 2 electrons there. The next 2 electrons are going to be here in this 2s sublevel. Remember, it's a little further away from the nucleus, a little bit more energy. So we got 2 electrons out here. And then we've got 2 and 2 is 4. 8 minus 4 is 4 electrons left. These guys are going to go in the p's. So we're going to go and put 2 in one of these p sublevels and then just 1 in the others. So we've got the blue, the green, and the pink color, and those are our purple, or those are our p's. So we've got 2p with 2, 2p with 1, 2p with 1. And again, you do 1 in each before you double up. Here's Hund's rule. Remember Hund's rule? You got to put 1 in each, up, 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 then you go down. So if I was to summarize this, remember this is the orbital diagram or orbital notation. It shows what's in each orbital. It shows what's in each seat. If I was to summarize this and write the electron configuration, then I just put the grand total, T-I-O-N, I just put the grand total in each section. So this would be 1s2, this is 2s2, and then even though we have 3 different p orbitals, I just summarize. I put 2p, 1, 2, 3, 4. And if we want to take this a step further and look at the valence electrons, I look whatever's in the outermost energy level. So the 2 and the 4, add them together, and it's 6. And if you look on the periodic table, which looks like this, sort of a rough drawing here. Here's a little helium. Here's the S block, here's the D block, here's the P block, and the F's are way down here. If you look, oxygen's going to be in group 6. It's got the 2 from the S over here, and it's got 4 from the P's. So it lands in group 6. Okay, just one more quick picture. I happened to see this somewhere, and I think it makes a good point. The red guys, or pink guys, are 4s, and the gray are the 3ds. Now, you know, hopefully, that the order that you fill everything in, you can just use the periodic table as a guide, but the order that you fill everything in is pretty easy until you get to 3p. After 3p, it gets a little challenging. So you would start with 1s2, then 2s2, then 2p6, then 3s2, and 3p6. So far we hit the first 3 periods, the first 3 rows of the periodic table. Then after 3p, if you think about where the periodic table is, actually let me just show you. If you're over here on the periodic table, right there, that's 3p. So where do you go now? Now you're over here in the 4th period doing the 4s 1 and 2. So after 3p goes 4s 2. Then after that, the next thing you hit are the D section, the D block. So this is D1 all the way up to D10. But the catch is, Ds are always 1 behind. So if you're in row 4, Ds are going to be 3. 3D 1 through 10. Over here it's going to be 4D 1 through 10. The next section is going to be 5D and then 6D. So Ds are always 1 behind. That's all you have to memorize, that they start up in the 3D section. So if we look at this picture, the red guys here, the pink guys, are the 4s, and the grays are the 3d. So we actually fill a lot of these pink guys. The electrons are zipping around here in this pink section, and it's really, really dense, pretty close to the nucleus. So they fill first, and then we fill the clover-shaped D block. That has more energy than the 4s does. 4s are actually closer to the nucleus over here, most of them. Remember, this is just 2 electrons. You can only fit 2 electrons in the S block. This is just somebody showing that those 2 electrons, at one point, one's here and one's up here, and then the next fraction of a second goes by, and now one's here and one's there, and then the next section or second goes by, and now one's here and one's there. So this is just a cumulative picture of all the locations that the electrons were in at any one point. So these 2 electrons spend a lot of their time close to the nucleus, but they do zip around out here because the 4s is pretty big, but it does, like I said, go much closer to the nucleus than the 3d here. So we've got 4s2 and then 3d max of 10, and then after that we start hitting the p block. So you would see the big p's like this, a little bit more energy than the s's. I didn't do a great job spreading them out, but you get the idea. 4p6, and then you go to 5s2, so 5 would be even bigger than the 4s would be, and so forth.